Hello everyone, welcome back to the Sagar Tech Kit channel. So in this video, we try to explore procedural assignment, especially blocking and non-blocking assignment. Already I gave some intuition about these in the previous video. So in this video, we'll discuss with some suitable examples and also good design practice we should follow while writing the Verilog code. So I hope this video is very useful. So you should know when should I use these blocking and non-blocking assignment statements, okay? Especially for sequential, to model a sequential circuit, we prefer a non-blocking. To model a combination circuit, we prefer a blocking statement. Okay, how do we avoid the race condition? We'll discuss in this video. See, simple example here. I have two concurrent always blocks with blocking statements. Now always at the rate passage clock A equal to B, always at the rate passage clock B equal to A. So what you understand, these are the two always block. It depends upon the what is the sensitivity list here, passage clock. So which one will execute first? We don't know. Yes sir. It will dependent. We don't know. So all always blocks will execute concurrently. Which one execute first? We don't know. Yes sir. Right? Now see, for example, either A equal to B would be executed before B equal to A or vice versa. Okay, we don't know, only God knows, okay, which always block will execute first. Either A equal to B would be executed before B equal to A or vice versa, depending on the simulator implementation, right? So the value of register A and V will not be swapped. Just now in the previous example, for example, it will execute first, okay? So B equal to 20, now A equal to 20. After that, A equal to 20, now if B equal to also 20, A, B, both values are 20. Okay, first it will execute first. For example, A equal 10. So I'll take, okay, I'll give, right, assume that here. For example, here A equal to 10, B equal to 20. Assume like this. Clear? First, this always block will execute. What is the B value? B value is the 20. Now A equal to 20. Immediately it updated. After that, this always block. By this, what is the value of 20? A 20. Now B equal to 20. So both A and B values are 20. In this case, both A and B values are 20 only. For assume that it will execute first. It will execute first. Now see, it will execute first. Assume that. What is the A value? A value is the 10. Now here B is equal to 10. After that, next. Here this is the next statement. What is the B value by that time? 10. So A equal to 10. So in this case, A comma B is 10. If you execute this always block first, both A and B values are 20. If you execute this always block first, A and B values are 20. So it is depends upon, what is that? It depends upon simulator implementation. Yes or no? And moreover, these registers A and B will not be swapped. Yes or no? Right? Understood. So how do I solve this problem? By using simply, this is known as a race condition. How do I solve this problem? Okay. How do I avoid this race condition? Simply by using the non-blocking statements. So here two concurrent always blocks with a non-blocking statement, always at the rate passage clock A less than or equal to B, always at the rate passage of clock B less than or equal to A. So in this example, okay, what is that here? Separating the read and write operations ensures that values of register A and B are swapped correctly. So regardless of the order in which they write, the operations are performed. Now see, if I take simple example here, same example if I take, assume that A equal to 10 and B equal to 20. Assume this first always block will execute. What is the value of B? Now B is the 10. So now B is the 10. It will store in some intermediate variable. We won't assign this B to the A immediately because it is a execute and zero simulation time. Then we'll have another always block. So we'll execute this always block. What is the value of A? A is, what is the value of A? No, sorry, here B. What is the value of B? B is the 20. What is the value of A? Here 10. Now after evaluating these expressions B and A, at the end of the current time step, then we are assigned. Now A is equal to 20. Now after that B equal to 10. Clear? Even though, for example, assume that this always block will execute first. So in that case, what is the A value? A value is 10. Yes or no? So what is the B value? B value is also 20. So now we are evaluating this. We are reading. Yes or no? We are reading this one. B is a 20, A is a 10. So now at the end of the current time step, we write this operation. So now A update is at 20 and B update is at 10. Clear? Even though if we change the order in which the right operations are performed, you can write this is first or this is first, or you can, the simulator will take this first or this first. All are same only. Clear? Even though if we change the order of this right operation, we'll get the same output. So good design practices. So do not mix blocking and non-blocking assignment in the same procedure block. So we need to follow these are mandatory rules. So do not assign the same variable from multiple always blocks. We cannot mix both blocking and non-blocking in the same procedure block. And also we cannot use same variable from multiple always block. We cannot use same variable. Okay, for example, if I use X in one always block, we cannot use this X in another always block. Now see some example. Now see here, I don't want to write a complete program, just I'll explain the concept here. Regex. Here one always block, always at the rate passage clock. Here also another always block. What is that? Assigning to X. We are assigning A to the X. Here also we are assigning B to the X. So two always block, that LHS variable is the same. We try to write two different values under the same variable, that two at a time. Okay. So do not assign same variable from multiple always block. This is not a good practice. We don't know. What is the problem with this? Okay, unpredictable synthesized results. We don't know whether it take the A value or B value. Some simulation synthesis mismatch. Okay, the simulation will get some output. After synthesizing, we are getting a different output. And most of the synthesizers will throw an error or warning if you write like this. Okay, so multiple write on the same variable. Clear? So simply for X we are connecting A and B. We are short, I think in case real time we say we are short circuiting A and B with X. Clear? Now see another here, always at the rate passage clock begin. So A equal to B and C. This is a blocking statement. D less than or equal to D. This is a non-blocking assignment. So we cannot mix these two. Clear? Like this. So what is that here problem? Mixing blocking and non-blocking causes the unpredictable simulation behavior. Okay, we won't find the actual output. Sometimes we'll get some output, other time we cannot predict actual output. Okay, can lead to the race condition also, and also synthesis mismatch. In the simulation we'll get some output, but after synthesis we'll get another output. So better to avoid mixing blocking and non-blocking statement, and also cannot use a same variable from multiple always block. Don't assign values to the same variable, okay, from multiple procedure blocks. I hope you understand. Okay, this is a good design practice. Now see, this is a simple example. So I hope you understand. Okay, this blocking and non-blocking. So try to analyze this simple code stepnet. So model evaluate to out. Now see here, output is okay, only one variable as output out. So reg A comma B C. So here initial, always initial. Okay, how many procedure blocks we have? So one initial block, one always block, one always block, one initial block. So we have 4 procedural blocks here. Now all will execute concurrently. Clear? But first we'll see. And what is the purpose of monitor? Monitor will execute, okay, whenever the ABC value changes, the monitor will execute in the current time step, but at end of that current time step, we can say, if ABC are changes, the monitor will execute end of the current time step. For example, ABC values do not change in that current time step. Okay, that monitor won't trigger, monitor won't execute. Okay, right. Anyway, so initial, always initial. We have 4 procedure blocks. Let's start with this initial. Okay, so how do we know that? So assume that first we'll start with initial. Okay, you can start with this also, right? Now A equal to 0, B equal to 1, C equal to 0. Clear? Now C is 0, B equal to 1, A equal to 0. After that, now we are go to this. C equal to #5 negation C. Nothing but we should wait till 5 time minutes delay. Oh, we are at 0 simulation time. So after 5 time step only it will execute. So now we'll wait. Clear? Then we'll go to this always block. So at the rate passage clock, at the rate passage C, nothing but if the C changes from 0 to 1, then only we'll execute this always block. As of now, what is the value of C? 0. When it should be a 1? After 5 time units of delay. Now this always block will also execute at the 5 time step. Yes or no? After 5 time unit delay only it will execute. Understood? Because the C will change from 0 to 1 at time step 5 only. Now it is also in hold mode. Assume that. So now initial, begin. So monitor will write. So monitor means if the ABC value changes, then it will execute in that current simulation time, current time step, sorry. Okay. Now at time equal to 0, A equal to 0, B equal to 1, C equal to 0, A equal to 0, B equal to 1, C equal to 0. Why this pointer will trigger? We have some default values A, B, C as X. Okay. Understood? Now if we change the value as 0, 1, 0, then it will execute at 0 simulation time. So what is this? Dollar time returns the current simulation time. Okay. Is here ampersand D. Okay. This is the returns current simulation time. Already we discussed in the data types, I think. Right. So time 0, A equal to 0, B equal to 1, C equal to 1. Now after 5 time step, what happens? C becomes 1. Because actually C is 0, 0 complement 1, C becomes 1. Now C changes from 0 to 1. Immediately, whenever C changes from 0 to 1, this always block will trigger. Clear? Because passage C, nothing but C changed from 0 to 1. So immediately by that time, what is the value of B? What is the value of B? B is the 1. What is the value of A? A is the 0. So now when this always block will execute, actually it is not in 0 simulation time. Now it is at time step 5. Clear? Now at the time step 5, any other statement? No any other statement, right? Now at the end of this time step 5, then A is updated as a 1 because B is 1. B is updated as a 0 because A is 0. Now next at the time 10 $stop. So 5, 6 there is no statement. 7th, 8th, 9th, 10 there is no statement. Yes or no? At the time step 10 we use the $stop. Now we are stopping this simulation. Understood? We are holding this simulation. We pause the simulation. If you write $finish, we'll complete simulation. You close everything. $stop means just will pause, hold the simulation. Now at time equal to 5, what is the value of A? A equal to 1, B equal to 0, C equal to 1. So at the time step 5, A, B, C value changed so that monitor will execute in the time step 5 also, but end of the time step 5. Remember that. So whenever the value changes in that time step, then monitor will trigger, monitor will execute at the end of that current time step. Yes, sir. So at the time step 5, the AB value changes, the monitor will trigger and display. So it wait till time step 5, okay, time steps 10, then we'll stop that simulation. Clear? So here step 1, just for understanding, is step 1, at passage C, at this passage C, the simulator evaluates the right hand side of non-blocking assignments. So at the passage C, at the time step 5, C changed from 0 to 1 by that time. So now the simulator evaluates these expressions, right hand side expression B and A, and schedules assignment to the new values at the end of the non-blocking assignment updated events. So this assignment is scheduled at the end of the time step 5 because this always block will execute at the time step 5. Clear? So non-blocking assignment schedule changes at the time 5. So now A equal to 0, B equal to 1. Okay, these are the just evaluation, but updation is at time step 5. So when the simulator activates the non-blocking assignment updated events, the simulator updates the left hand side of the each non-blocking assignment statement. So assign the values, A is the 1, B is the 0. Here this is the read values of A and B. Okay, at the end of the time step 5, we are updating these A and B value with the new values. I hope you understand, okay, this example. If not, please pause the videos, try to understand, okay, by executing, by analyzing each and every statement in this module. Now see this slides taken from MIT. So now see, this is a simple conceptual need for two kinds of assignment in always block, okay. So anyway, initial is not synthesizable. We never prefer initial, okay, procedure block for designing any model. That initial is only for test bench purpose, for simulation purpose only. So now if I want to swap this, okay, two numbers, okay, so blocking, evaluate and assignment are immediate. If I use the blocking, immediately will evaluate and assignment. Just now we see A equal 20, B equal 20, or A equal 10, B equal 10, like that we'll get. We won't get these values are not swapped. So now this is not suitable. The blocking statements are not suitable for this type of modeling. Clear? So now here you can write a b c. So x equal to a and b and y is equal x or c. So we need to evaluate immediately. Whenever a or b changes, immediately we need to evaluate this expression, assign to the x. Then x as a input to this OR gate. Immediately the updated value of x we consider to find the value of y. Clear? So y is equal x or c. So what is this x? We need to update it based on the a and b. Whenever a b changes, x should be immediately updated. Okay, like so this type of to model this type of circuit, we are using blocking statement. What is this? This is a sequential circuit. It holds the values. Yes or no? Swapping means we need to store in some intermediate variable. Yes or no? So here simple combinational circuits. So in case of non-blocking, assignment is postponed until all RHS evaluations are done. So here this assignment is postponed, okay, until we complete this RHL evaluation. Yes or no? We need to read the B value, we need to read the A value. At the end of the time step, we need to assign. So now in this case, we'll use a non-blocking statement. This is a correct way. Okay, where in this case, if you want to model this type of circuit, we'll use the blocking. So by this, so when should I use this blocking and non-blocking? Now see, so this non-blocking is used to sequential circuit. These blocking statements are used to combinational circuits. In other way, for a sequential circuit logic design, we use non-blocking statement, whereas the combinational circuit, combinational logic design will use a blocking statement. Now see, for example, I want to design this combinational circuits. Just now we discuss which statement we prefer, blocking or non-blocking statement we prefer. So like simply we can write, so model blocking, input a, b, c and output reg x comma y. Okay, so now always at the rate a comma a, b, c changes, then we evaluate x, a and b, this x, a and b, and we should find the y, x or c. Y is equal x or c. Okay, this is a correct way to write a Verilog code for a given design. Okay, digital design. Understood? So now this x and y should be reg type. Already we discussed that LHS in the procedure block always is a reg type. Clear? So default all are y type. If you want to use as LHS variable in the procedure block, you should declare those as a reg type. Clear? For example, if I write like this, same code if I write module blocking input a comma b, c, output reg x comma y. Always at the rate a comma b, c begin. X less than or equal a and b. Y less than or equal x and c, x or c. X is not updated immediately here. Y use the old value of x. Here we use the updated x value to find the y. But here we use the old x value, okay, to find this y. So now if you see this, the circuit like this. So we'll get some x value by changing the a and b, but we won't use this new x value, the previous time slot, whatever the old value we have, that we'll use to find the y. Okay, so now if you write a code, we'll get a, okay, this is the actual digital design, not actual, this is the, okay. So but we need this, means you should write. So for combinational circuit, we always prefer blocking statement. For sequential circuit, always prefer non-blocking statements. Now see this example. So I have used two models here. One model, non-blocking out in clock. Okay, input in and clock, output reg, okay, out. So I declare those as a input and outputs. So reg q1 and q2. So now see, simply always at the rate passage clock begin. Just these are the non-blocking statement. These are the blocking statement. Everything is same. Now if I execute, if I simulate, what my synthesis tool will, okay, here if you see this, here are 3 flops, where if I synthesis this, only 1 flop. Clear? Now see, so why it happened now? Here this q2 hold the old value of in, whereas the q1 is hold the value of q2. That means previous value of q2. How to hold the old value of q1, previous value of q1. q2 is the previous value of in, q1 is the previous value of q2, out is the previous value of q1. Then the end of the time step will assign. But in this case, what is that? Now we'll evaluate this expression. Okay. For example, assume that, I'll give a simple example. Assume for example in this case in is equal to 0. So in this case in is equal to 0. Clear? Assume that. So what is the Q2? Immediately Q2 is updated as a 0. Yes or no? So now Q1 is equal to Q2. What is the Q1? Q1 also 0. Clear? What is the out? Now out is equal to Q1, out is equal to 0. Clear? So now this Q1, Q1, Q2 out all will hold only one value, 0. So now Q2, Q1 out hold one value. So only one flop, it infer only one flop. Okay, only one flip-flop it infer. Here 3 flip-flop it infer because this Q2 hold the previous value of in, old value of in. Yes or no? So Q2, Q1 is old value of Q2. Out is old value of Q1. So we have 3 different values. So we need here 3 flip-flop. So now see a synthesis RTL diagram. For this code, we have 3 flip-flops. Whereas for this, we have only 1 flip-flop. I hope you understand. Clear? So now, if you use a non-blocking, it infer 3 flip-flop. If you use a blocking statement, it infer only 1 flip-flop. Clear? So now see another example. See here, the order does not matter. You can write in any order. You can write Q1 equal to Q2 first. After that, Q2 less than or equal to in, or out less than or equal to Q1. You can change the order of these statements. It doesn't matter, we'll get the same output. It infer only 3 flip-flop. But if we change the order, okay, sometimes maybe it infer 2 flip-flops, sometimes maybe 3 flip-flop, maybe 1 flip-flop. Based on the order we'll get. Clear? So now we'll check that also. In the next example, now see the simple non-blocking statement. This non-blocking, this actually blocking. Okay, example. Now see here, Q2 equal to in. Assume that in equal to 0. So Q2 how much? Q2 equal to 0. Q1 how much? Q1 equal to 0. Out equal to how much? 0. So it infer how many flip-flops? Only 1 flip. It hold only one value, that is a 0. Clear? So it infer, see how many flip-flops? It infer only 1 flip-flop. It infer only 1 flip-flop because all variables Q2, Q1 hold only in. Yes or no? All variables hold only one variable in. But if we change this order, okay, if we change this order, okay, we'll get a different RTL, okay, different synthesis output. Clear? Sorry. Now in this case, if I write like this, see here I'll change the order. Now in this case, the Q2 is in. So here Q2 is in. But what about the Q1? Q1 is equal to Q2. Okay, here first of all, I'll explain clearly. So now Q1 hold the Q2. Q2 hold the in, but out hold the Q1. What is the Q1? Q1 means Q2 only. So out and Q1 hold only one value Q2. Whereas the Q2 hold the another value in. So now Q2 hold in and Q1 and out hold the same values. But he required only here 2 flip-flops. It infer only 2 flip-flops here in this case. I hope you understood. Now see here in this case, out is equal to Q1, whereas the Q1 is equal to Q2, Q2 is equal to in. Clear? So out is equal to Q1, whereas the Q1 is a Q2, Q2 is the in. So we have 3 different values. We are holding 3 different values. Out, Q1, Q2 as hold different values. So how many flip-flop here? We required 3 flip-flops. Understood? If we change the order of blocking statement in the procedure block, we'll get a different output. The synthesis tool will give a different netlist. Clear? So now to avoid all these, better you'll use non-blocking statements. Okay? For designing model sequential circuit. Whereas to model a combinational circuit, we'll use blocking statement. In this video, we discuss various procedural assignments like blocking and non-blocking statements. You should know when should I use the blocking and non-blocking statements, and also how to avoid the race condition. For example, if you want to design any sequential circuit, we prefer always a non-blocking statement. If you want to design a combinational circuit, we prefer blocking statement. And also good design practice, we never mix both blocking and non-blocking in the same procedure blocks. So I hope you understand what is meant by blocking and non-blocking statement. Where should I use, how to use this blocking and non-blocking statement, okay, in Verilog. Thank you very much.